Welcome back to my channel. Today we will discuss about the ID versus VDS. And in last lecture we have seen the Mosfet structure we have seen, and Mosfet working we have seen, as well as the derivation of drain current. Okay, so that we have discussed already. So today we will go through uh, ID versus VDS. Okay, so that is the agenda of today. So in last lecture we have derived ID. So let's write that equation. So it is mu n cox w by L and then VGS minus VTH mm, VDS in multiplication minus VDS square divided by 2, right? So this is the equation of parabola. So if you will plot ID, whenever you want to plot ID versus VDS or you want to plot ID versus VGS, you have to keep another other parameter constant. Like you want to plot here ID versus VDS. So you have to take constant what? VGS. VGS you have to take constant. This is your first step. And this VGS is greater than VTH. Okay, means MOSFET is on. Okay. So let's draw ID versus VDS. This is ID and there VDS. Okay. So now ID will increase, ID will increase. Sorry, with VDS ID will increase. Okay. So how it will increase in a parabolic way like this, and it will achieve some maximum value, that is at some VDS and one value. Okay. Let consider I am giving here VGS equal to VGS1 I'm giving. Okay. Now I want to know that what is the value of VDS1 at which my current is the maximum. So for getting that value of VDS1, we have to, maths. By maths, we know that you derive it, der do derivative of this equation with respect to the VDS and put it equal to 0, you will get the maximum value of sorry, the value of VDS at which you will get the maximum ID. Okay, so let's do the differentiation. So the first term, this one term, I'm taking one another color. So this term is constant, so it will be like mu n cox w by L, right? Then this is also constant, so it will be VGS minus VTH, and the differentiation of this will become 1. Okay, now minus. What about this? We will differentiate it with respect to VDS, so it will become 2 VDS divided by 2. Okay, so it will be cancelled out and put it equal to 0. And when this constant term will go on right side, it will become 0. So the remaining terms are VGS minus VTH minus VDS divided by 2. Sorry, not 2. It was cancelled. 0. So VDS will become equal to VGS minus VTH. What was the value of VGS? It was VGS1, so keep it VGS1, and the VDS, I was keeping VDS1, the maximum value. So at VDS, when the VDS equal to this, that time I'm getting the maximum value of current. So the VDS equal to what? VGS1 minus VTH. Okay. So if I let consider the VTH is 1, I'm considering here VTH equal to 1 and VGS 1 equal to, I'm keeping 3. Okay, so VGS, now I'm considering that VGS2 which is less than, now I'm keeping VGS equal to VGS2 which is less than VGS1. Let's consider it is 2. Okay, so it is 2. So now see. So where this point will come, where we will go to the maximum value, here or on right side, where we will go. So on left side, because you can see that subtract this, you will go 2 by this. If you will do, it will become 1. So it will go on left side. So there, okay, somewhere there we will achieve. Okay. Now the second thing, it will go on top or lower side. So we have to calculate for this the maximum value of current also. So you have to put this value VDS equal to VGS minus VTH in equation this, and you will get the maximum value of ID. So what will be the maximum value? Let me put here ID max. I'm writing ID max equal to mu n COX W by L, and it will be VGS minus VTH square, and there it will be 2. You can do it. Okay. This is VGS minus VTH, so it will be square, then minus VGS minus VTH square divided by 2. And you will subtract from this, it will become VGS minus VTH square divided by 2. That 2 will come here, so it is that. So this value is this VGS1. So it will be what? Let's consider this initial term K. So it will be K into VGS1 minus VTH. Now for this, if I'm reducing VGS I kept 2. So this value will also reduce. So the maximum value reduce. So it is K VGS2 minus VTH. Okay, so it will go like this. Now the third case I'm taking. If the VGS3, I'm giving now VGS3, okay, which is greater than the VGS1, greater from all of those two which I have given recently. Okay, so the it will go to the right side. There it will come, right? And the maximum value of ID will increase. Okay, so it will be somewhat like this. Okay, so this is all. I hope it is clear. So now let's go to the next one page, and there we can discuss one more thing. So, okay, I'm making the plot again. This was ID, this was VDS. Okay, so we have learned till now that uh, that plot we have learned that at what value of VDS we got the maximum value of current. That only we learned till now. Okay, so now the second point, what we will learn here. So there you can see ID is 0, right? ID equal to 0. But VGS is constant here also. Okay, which is VGS is greater than VTH. Means what does it means? Means MOSFET is on. MOSFET is on. Only the current is 0. That thing. Okay. Now this is the second point. Hope it is clear. Now the third point. In third point, what we will see. Okay. So as you know, I'm writing current equation on top. ID equal to. I'm keeping this mu and COX W by L as K. Okay. And inside it was VGS minus VTH, then VDS minus VDS squared divided by 2. I'm saying when this one is very small as compared to this, I mean VDS square divided by 2 very less than VGS minus VTH divided by, sorry, VDS multiplication. What will happen? So you can neglect this, right? If you can neglect this, ID will become equal to K, then VGS minus VTH, VDS. Simple. Okay. So you can see ID is linearly proportional to the VDS in this case. Okay. And you can write this like that also. How? You can cancel these. Okay. And then VDS less than 2 VGS minus VTH. So when this is the case, okay, this will be the situation that ID will be the linear to the ID VDS. Okay, what does it mean? Let's plot the graph. So in graph, this is VDS, this is ID, and there somewhere there is VGS minus VTH on which we are getting the maximum value of ID. Then okay, this is like this. Okay, so I'm taking one another pen. This one. Okay. So in this area, let's take this is the area in which VDS square VDS is less than very much less than the 2 into VGS minus VTH. Okay. So in this case, ID is linear to the VDS. That is the thing only. Okay. So in this case, ID is linear to the VDS. As VDS will increase, ID will increase with respect to the VDS linearly. This is the third point. Okay. I hope there will be no issue. So now we can see one more thing here. You know that V equal to IR, or you can say I equal to V by R. So can you compare this equation with this equation? Okay. So let's do. ID will become equal to VDS, that is the V, okay, and this we will to keep 1 by R, okay. I mean we have to keep it on in down, so it will become like okay, okay, VGS minus VTH. Okay, this. Any doubt? No. Okay, so we have this equation. Good. Now this is ID equal to 1 by what is K? Mu n COX W by L, then VGS minus VTH. And there it is VDS. Okay, we can write that equation like this also. Okay, I mean like this. Sorry, 1 by. Okay, see, sorry. Okay, 1 by this. Okay, so V was equal to IR and I was equal to V by R. So what is R? Compare these two. You will find out that R equal to 1 by mu n COX W by L VGS minus VTH. See, it is 1 by mu n CX whole. I'm keeping whole in bracket. Okay, I'm writing it again. Okay. Hmm. So, okay. So there it will be like this. Uh, hmm. Mu n COX W by L VGS minus VTH. Okay, like that we can write ID. And then you can compare with it with this equation, second and one. And this give us that R equal to this. So this R we can give name R1. Okay. Okay, so let me take one another page. So what does it mean R not R on? Okay, so it means we okay, let's see, we have a MOSFET and there is a gate voltage and VDS. So it is like this. There is a R on. Okay. If R on is infinity, when can be the R on infinity? Okay, when the VGS equal to, I am writing again R on. R on equal to 1 by K VGS minus VTH. You know the K is mu n CoxW by L. If VGS equal to VTH, then R on will be infinity. Infinity means there will be no passing of electron and there will be no current. No current will pass. So ID equal to 0. Okay, and it is obvious when uh, VGS is less than equal to VTS, then the current is 0. Okay, so and when the VGS is greater than VTH, then there will be some R on and there will be some current. So there the MOSFET is like an switch. Okay, so see, if R on VGS is greater than VTH, then you can think it is short circuit. No, there will be some resistance. Okay, so how it will be? The switch will be like this. When it is short, the MOSFET, but there is some resistance like this R on, and this is a switch MOSFET like a switch. Okay, and in case of open circuit, it will become open circuit. Simple. Okay, so these are the two cases. Let's go to the next page. So we have seen ion. Ion was like this. We have went up to this. What after this? VGS minus VTH. This is VDS. This is ID. What after this? How this will follow? Will it fall down or not? No. The answer is no. Why? Let's go to the device first. To understand it, we have to go to the device and let's make MOSFET. This is N plus, N plus, okay. And there is gate, okay. So there I'm giving VGS and here I'm giving VDS. So see the potential difference, we have already seen that potential difference will be highest there as compared to here, and this will be lower from as compared to here, and so on. So the lowest potential difference will be on this side. Okay. So the charge in channel, how it will be? I'm taking this is L, this is 0, this length is L. Okay. So there will be maximum Q channel, I mean charge in channel, and it will reduce with L. The minimum charge concentration will be at L. Okay. So we can make it like this. I'm taking one another man for showing the charge concentration like this somewhat. Okay. It will be like this. So if you will increase the VDS, what will happen? Again, I will change my pen. Okay, I'm taking pink. So I'm increasing VDS. What will happen? This point will shift where? There. And this point where the potential is becoming zero, there is no charge. That is called as the pinch off point. Okay. So that pinch off point shift to the left if I'm increasing the VDS. Okay, but in reality, that will shift very small distance. Okay, so it will shift like this, and this slowly it will move. Okay. So the equation which we have used previously, that which was giving us the current equation. So that is not applicable in this case. Okay, so we have to derive the current again. So see at the end point there, what is the potential difference? So the potential difference is VGS minus what? VDS equal to VTH. If this is the case, okay, this is the case, then there will be some 1 2 electron will be there, free electron. Okay, no more. And we can write it like that also. VDS equal to VGS minus VTH. So what is this? This is the potential difference. Okay, VGS minus VDS. This is the potential difference there. On the top you can see there is VGS and here you can see there is VDS. So what is the difference? VGS minus VTH, and is equal to VTH. Means it's on the boundary. Below this is no channel formation. Above this there is channel. So there will be 1 2 electron. So we are considering this. The difference is equal to VTH. Okay, we can write it VDS equal to VGS minus VTH also. The boundary we are taking. So now what? So we have to derive the current because that the way of derivation as we did previously is not applicable here. So okay, let's do it. ID equal to K. I'm keeping mu n C ox W by L. I'm keeping K. Then VGS minus VTH. Okay, minus Vx. If you remember, if you don't, you can go to my previous video lecture, I guess second. You can see the derivation there and how these things are coming into picture. Okay, dvx and integrate it 0 to vds. But what is vds now? It is vgs minus vth. Okay, so let's do it. A into vgs minus vth integration of dvx 0 to VGS minus VTH minus integration of integration 0 to VGS minus VTH, that is Vx minus, sorry, no, dVx. Okay, so what will happen now? Let's integrate K. It is VGS minus VTH and it will become VGS minus VTH only. Why? Because differentiation of this thing will become Vx only, and you have to put the upper limit minus lower limit, so it will become Vgs minus Vth only. Okay, now it will become the integration of this will give v square x by 2. Okay, you can put the value of v square, so it will become Vgs minus Vth square by 2. Okay, like this. Now, so let's write the value of k also. Mu n cox w by L, and it will become VGS minus VTH square. Subtract it, it will become VGS minus VTH square by 2. Okay, now let's keep this 2 outside of this and remove this also. Okay, there I'm keeping ID. So this is ID. So you can see by this that ID is independent of VDS. Okay, what we observe from this? ID is independent of VDS, means ID is constant. Okay, so now let's plot. VDS and ID, it will go like there. It is getting maximum value, VGS minus VTH, and will become constant. Okay. And what is the value of this constant? Mu n by 2 cox w by L VGS minus VTH square. This is the value. Now, this region is called saturation region. Okay. And this region called as linear region. And there is one more region which is called cutoff region. What is cutoff region? In which MOSFET is off, its VGS is less than VTH. That is the cutoff region. Okay. So what we have learned today in this lecture? In this lecture, we saw first, mm, yeah, ID versus VDS, how to plot ID versus VDS, and how to get the maximum value of ID, max value ID, and at what VDS value. That we have seen the first point. Second point, we saw linear behavior of ID, linear behavior of ID with respect to VDS. Okay, this is first observation. This is second, and third we saw Aaron. Okay, and fourth we saw what? Yeah, uh, complete ID versus VDS graph. Okay, that much we have seen. Okay, let's see one more thing. One last thing we can see. See, what was the equation? Uh, okay, so when the VDS is less than VGS minus VTH, that case, and one case is VDS greater than equal to VGS minus VTH, that case. So we have seen, we did deri all derivations. Okay, for this case, ID equation was what? Mu n cox, sorry, not on down, cox w by L VGS minus VTH, and then VDS minus VDS square by 2. Okay, and for this condition, ID was mhm, ID was equal to mu n cox w by L and VGS minus VTH square, and there was 1 2. So this equation is not applicable here. Okay, right? And this is called as active region, linear region it is called, and this is called saturation region. 1 point. Okay, one more thing we can see, one last thing, that is, let's write again. ID equal to, ID was directly proportional to the mu n cox w by L. We saw till now. So if we are increasing the mu n, ID will increase. Is it true? So see, mu n is equal, mu n is what? It is mobility, mobility of electron. So if mobility will increase, velocity will increase means ID will increase, simple. The first. Then the second, COX. If COX increasing, you know the Q equal to CV. Okay. Then C is A into COX. Okay. If COX increasing, this will increase, it will increase, then Q will increase. If Q is increasing, then ID will increase. Now the third, if W increase. Okay. If W will increase, then ID will increase, obviously. Why? Because the charge will increase. And there is a big path. The path will increase, so more charge particle can pass easily. So ID will increase. Okay. There you can write ID will increase. Fourth one, L. If L increase, ID will reduce. Why? Because in MOSFET you can see Okay, this is L. It is like an resistance. Okay. If this will increase, then resistance will increase. If resistance will increase, then ID will reduce. So this is all you can see from device level also. Okay. So that's all for today. Thank you for watching the video. And if you have any doubt, you can comment me. And if you need notes of this, you can comment me. I can share notes also. Yeah. Okay. Thank you. Let's meet in next video.